give this third talk. So I put up here on my camera the flatness criterion, which I derived yesterday. Yeah, that was my main message, is that we're doing geometry using sheaf theory and stability, semi-stability for sheaves. And the main flatness criterion on singular spaces, which I proved or sketched the proof of yesterday, is the following. I'm working on a terminal projective variety, so a variety with terminal singularities. And I motivated this class of singularities, say, by the minimal model program, or for Fanos by the quest of compactifying the moduli space of, say, Kähler-Einstein Fanos. And I take a sheaf, which is constructed as follows. I take a locally free sheaf on the smooth locus, and I push it forward to the whole variety, and then it's no longer locally free necessarily, but it's reflexive. Yeah, and I explained what that is. And now I make, okay, that's a general setup, and now I make 3 assumptions, so in 2 groups. So the first one is an assumption on the variety, namely I assume that this variety is maximally quasi-étale. In the notation of yesterday, this means that x is equal to x hat. And so x hat was this finite cover which got rid of all the difference between the fundamental group of the regular locus and the fundamental group of the whole variety, at least as far as representations are concerned. So this means on X, I assume that if I have a, say, a flat vector bundle on the regular locus of X, it will extend to a flat vector bundle on the whole of X. Okay, that's an assumption on X, which I can guarantee after going to a finite cover, quasi-étale cover. And then I make, okay, 2 assumptions on the sheaf. It's H semi-stable for H an ample divisor, and that the discriminant vanishes. Yeah, I wrote here, in general, for a semi-stable sheaf, this discriminant will be bigger than or equal to 0. So I'm going to the extreme case. And I also recalled what the discriminant is. It's made out of C2 of F and C1 squared of F. And I explained how to define these intersection numbers with h to the n-2 by restricting to a surface where everything is smooth and locally free. And then I have 2 coefficients that I have to put. That's 2 times the rank of f, and here I have rank f minus 1. And so I also explained that this delta of f is nothing but the C2, the second Chern class of the endomorphism sheaf of f. Well, okay, and that leads to the fact that f and hence ndef is semi-stable, and then the endomorphism sheaf has C1 equals C2 equals 0, and then the statement is, under these assumptions, ndef is a flat vector bundle. Yeah, so it's a vector bundle, so it's locally free and it's flat. So it's given by representation. Okay, that's the reminder from yesterday. Share my new slides. Yeah, so I will now talk today about the geometric applications, which are very close to what Henri explained to us, where he explained the use of Kähler-Einstein metrics, and I'm trying to up to a certain point avoid this issue of the existence of Kähler-Einstein metrics. And I'm going to use sheaf theory for Fanos. Okay, so here's the definition for the class of varieties I'm going to work with. A variety is called Q-Fano if it has at worst KLT, so Kawamata log terminal singularities. So in particular, if I have terminal singularities, these are KLT. And then the Fano condition is that minus Kx. Yeah, KLT means in particular that minus Kx is a Q Cartier divisor. So I can talk about ampleness, meaning that some locally free multiple of mk minus kx is actually ample. So that's these are the varieties I'm going to be interested in, and there are a lot of examples. We've heard of them. So certainly Pn is the first example. It has minus kx equal to OPn n plus 1, and therefore Fano. It's smooth. Hypersurfaces of degree less than or equal to n in Pn are Fano. And these are also smooth. The general general smooth hypersurface of degree n less than or equal to n. Now but I also have singular examples. Every time I have a group G, a finite group, sitting inside the projective linear group, acting on Pn without fixed points outside a set of codimension bigger than or equal to 2, then the quotient is Fano. Yeah? So this is because essentially the canonical bundle downstairs is, if you pull it back, you get the canonical upstairs. Because of this codimension 2 condition. And then the singularities are KLT because they're quotient singularities. And so you see you get a Q Fano. Yeah, so here's a specific example. Actually, there are many more. So you take Z divided by 3Z and you act on P2 via this. You take a third root of unity, and then you don't act in the first coordinate, homogeneous coordinate. You act by psi to the m in the second and psi to the 2m in the third. And that's fixed point free outside. So it's free outside a finite set. And then the quotient is a Q Fano surface. And so actually, there are many, many examples of this kind, x equal Pn mod G. So one slightly surprising statement is that if you take a non-abelian simple group and you take any representation of that non-trivial representation of this non-abelian finite simple group, then you add sort of compactify this representation by adding a trivial factor and then taking the projectivization. So you get an action on Pn, and then you take the quotient, and it fulfills this property of being fixed point free in codimension 1. Okay, and Henri already told you that if there is a Kähler-Einstein metric, you have this so-called Miyaoka-Yau inequality in the Fano case. And it reads like this, n divided by 2n plus 1, and then c1 squared times minus kx to the n equals to 2 times minus kx to the n minus 2. Moreover, if equality holds, then you have constant holomorphic sectional curvature, which in this sign means that, so positive sign means that x has to be equal to Pn. Yeah, so this is a uniformization result because essentially it says something about the universal cover, but here we are in a world where all the manifolds are simply connected, so that's why you don't have any quotients in this smooth case. Okay, so a couple of remarks. Well, I think Henri explained extremely well what a Kähler-Einstein metric is. Just sort of a quick reminder, it's a Kähler metric with certain symmetries in the curvature tensor. And the main message also is that not every Fano manifold admits a Kähler-Einstein metric. The example of a blowup of P2 in a point was already given, which has non-reductive automorphism group, and hence it cannot admit a Kähler-Einstein metric. And now, I mean, there has been tremendous success in understanding the conditions, the algebraic or algebrogeometric conditions that are equivalent to existence of a Kähler-Einstein metric. This is the theory of K stability or K polystability, which decides about the existence, but this is extremely hard to check. I mean, very recently, people have made some progress, but still, it's very hard to check for individual examples whether this K polystability is fulfilled. Okay. Looking at this inequality, this Miyaoka-Yau inequality in the Fano case, really the Kähler-Einstein condition is somehow necessary, or some condition is necessary, because not every Fano fulfills this inequality. Yeah, again, a compactification of the total space of a line bundle is a counterexample. So X, the projectivization of this O of 3 plus O over P3, this is a fourfold. This does not satisfy the inequality. And I will call this inequality here, this Miyaoka-Yau inequality, MYF. Yeah, Miyaoka-Yau and then sub F for Fano version. So this violates the inequality, and also our nice previous example about which I gave. So this time it's about the total ambient space. So Y, the weighted projective space with weights 1, 1, 1, 3, or equivalently the cone over a degree 3 Segre embedding of P2. Also, it's a Fano, it's a Q Fano, but it violates this Miyaoka-Yau. So the question is, what is the correct condition? And okay, the message is already clear. It's some sort of semi-stability condition for this Miyaoka-Yau inequality to hold. Yeah, so what is the additional condition you have to impose? And so for that, I make the following key observation, which seems small, but is somehow for us, for me, it was a really important observation, that the Miyaoka-Yau inequality looks like the Bogomolov-Giesecker inequality for a semi-stable rank x plus 1 sheaf. So let me show you this on my using the camera. Yeah, so I've written both inequalities next to each other. Yeah, so here was the Bogomolov or Bogomolov-Giesecker inequality, and here is the Miyaoka-Yau in the Fano case. Okay, so you suspect that H, the ample bundle, should be minus kx. Okay, that's good because your Fano minus kx is ample, so that's good. Then you think that you have C1 and C2 here, but here it's of TF. So you could think that F would be the tangent sheaf. But then, okay, if you shift around these terms, so remember here, this is in general bigger than or equal to 0, and then you shifted the terms around so that you have C1 squared on one side and C2 on the other side. So this inequality is the correct inequality with the correct signs. The only thing that is not correct is that here the rank of F appears as two times the rank of F as this coefficient, and then rank F minus 1. Whereas here, you have something, if the tangent has rank n, you would expect n minus 1 over 2n here. So there's a shift by 1 in both numerator and denominator. Yeah? So it cannot be a Tx that is playing a role here. What you want is, so the message is, this looks like the Bogomolov-Giesecker for a rank n plus 1 sheaf having the same C1 and C2 as Tx. Yeah? Note that the most obvious sheaf of this form, namely T is Tx plus Ox. Yeah? This has C2 the same as Tx, because if you think about it, okay, you can imagine for all practical purposes that computing C2 has to do with writing this as a sum of line bundles. Okay, you write Tx as a sum of line bundles, and then you just add a trivial line bundle, and then you write this product, which where you add a trivial factor coming from this, and then the C2 does not change. Yeah, but this is not a semi-stable bundle because Tx, the C1 of this bundle is the same as the C1 of Tx. So Tx destabilizes this rank n plus 1 sheaf. So this is not semi-stable. Yeah? So you need an idea. And actually the idea or the solution has been there for a long time. Once you search for it. Yeah, so you search for a natural rank n plus 1 sheaf on X whose semi-stability is the correct condition to impose. Yeah, with the same C1 and C2 as the tangent.
Let me guess, the T extension.
That's true. Yeah, so this is the so-called canonical extension, which was discussed by many people in the past. So my setup is as before. So I have this Q Fano and this dimension n. So as I explained, xklt in particular implies that minus kx is Q Cartier, i.e., okay, this should have a minus somewhere here, d equal minus mkx is Cartier for some m. So Ox of d is locally free with some transition functions. Yeah? So g alpha beta. And let me be as explicit as possible. So then I can produce a first Chern class in this space by taking the transition functions and taking d log of them. So d g alpha beta over g alpha beta. This numerator is a one holomorphic one form. So this is a Czech cycle, and then if I take the class, a Czech cohomology class in h1x comma omega 1 of x. This is called the first Chern class of D, and okay, I had to take this multiple m, so I divide by m, so I get something which I call C1 of minus kx inside h1 of x comma omega 1 of x. Yeah, so I look at the first Chern class, and so I observe that this h1 omega 1 is the same as x1 ox comma omega 1 of x. Yeah, this is just because these are two derived functors, h1 and x1, from the same, coming from the same functor essentially. And so they are isomorphic, these cohomology groups. And so this means that my first Chern class here gives me an extension, yeah, of this form. So minus kx, C1 of minus kx defines an extension of the form 0 goes to omega 1 goes to w, that's the extension, goes to O of x goes to 0. Yeah, and so now we have to be a little bit careful because we are on the singular space. We have to control a little bit the singularities, and hence the following property is crucial. So if I take any affine subset, open subset in X, then of course, because it's affine, H1 of U with values in the restriction of omega 1, it's 0, yeah, because it's affine. But this means that if I restrict this extension up here to this U, there the extension class will become 0, and so the extension will split. Yeah, so this means the extension is locally split. And because, I mean, I have to be a little bit careful because this omega 1 of x, remember we're on a singular space. This is a, I would say, highly singular coherent sheaf. Yeah, this will have torsion. This will have co-torsion, meaning that if I look at the natural map from omega 1 of x to its double dual, it will neither be injective nor surjective. So a lot of potential problems lurk in the background. Yeah. But okay, this extension is locally split. And so I take duals. And because my extension is locally split, after dualizing, I still get an extension. I still get a exact sequence with zeros on both sides. Yeah, taking HOMS is not exact, but here, since I'm dealing with locally split extension after taking the dual, I get another extension, and this time it's an extension of OX by TX. Oh. Okay, some small analysis of this. So this E of X is the dual of W, and we're working on a normal space. Yeah, so this EX is HOM from W into OX. Okay, now X is normal. This means that OX is actually a reflexive sheaf. Yeah, so this has to do with the fact that on a normal space, regular functions on the smooth locus extend automatically to regular functions on the whole variety. Yeah, so this means that this EX is reflexive, which is very good because reflexive sheaves were those that we've been dealing with all the time, and it's of the form that we've been discussing. It's a vector bundle on the regular locus, where it's an extension of OX and the holomorphic vector bundle TX, and then you push it forward to X. Yeah, so, and this EX is called, I call it the canonical extension of X, or this extension, yeah, this exact sequence, we call it the canonical extension. And we are not the first to look at this. it's the, I mean, if you go and consider line bundles here as principal bundles, it's the ATIA class, the XTIA extension. Donaldson has looked at this while discussing how you can phrase the search for optimal metrics in a given Kähler class using this extension and some geometric spaces derived from it. Tian has studied it in a paper in 1992 about the stability properties of tangent sheaves of Fano manifolds. And also I have written a paper with Michael Wong where we point out, and okay, this is not surprising, but I mean, that you can also, you still have this extension in the Kähler case, and it has very nice geometric meaning for questions which have nothing to do with what I'm going to talk about today. Okay, so you've seen this extension many, many times. For example, if you do it for Pn, you get the Euler sequence. Yeah, so you get this canonical extension sequence is the Euler sequence. So E sub Pn is nothing but a direct sum of O of 1s, namely n plus 1 copies of O of 1s. And I point out that that's semi-stable but not stable. Yeah. Okay. So that is the main player in my game. And as I said, after you found this extension, things actually just fall into place. Yeah. So as you can see from the following proposition, now I'm back in my situation where I assume terminal instead of KLT. So I'm looking at the terminal Q Fano. Let me comment that the terminal condition is just to have a non-singular in codimension 2. So singularity starting only in codimension 3. If I'm not assuming terminal, but just KLT, I have to work with orbifold Chern classes. Yeah, so now if you assume that this extension is minus kx semi-stable, then the Miyaoka-Yau inequality holds. So the correct condition for the Miyaoka-Yau inequality to hold is exactly somehow semi-stability with respect to minus kx of this canonical extension. Yeah, and the proof is easy. After I observed this comparison, which I made using my camera a couple of minutes ago, namely that we already know that the Miyaoka-Yau looks like the discriminant of a rank n plus 1 sheaf with the same first and second Chern class as the tangent. Yeah, and so yeah, so you see, instead of taking a direct sum, my extension is an extension of OX by TX. So really the first and second Chern class of EX are those of TX. Yeah, because I'm making an extension with O. Yeah, okay, and then so the proof is exactly this. The Miyaoka-Yau holds if I interpret these intersection numbers according to my definition. I have to cut down to a surface which is coming from the complete intersection of n minus 2 copies or members of m minus kx. And then this holds if and only if delta of Ex restricted to S is bigger than or equal to 0. But Mehta-Ramanathan and Flanner implies that if my Ex is minus Kx semi-stable, the restriction to a generic surface of complete intersection surface of a sufficiently high degree will be semi-stable, so the Bogomolov inequality yields the result. Yeah, so the Bogomolov inequality for a vector bundle on a smooth surface yields the result. Okay, good. Yeah, so once you have this, it's easy. So how do you look at this condition, or is this condition always fulfilled? No, it's not. Do you have examples? Actually, in the case of smooth Fanos, this is one of the results of Tian in this 1992 paper, that if you have a Kähler-Einstein metric, then this is semi-stable, and actually you can put something in between, and that's very recent, based on work of Chi Li, so we have the following chain of implications. X has a Kähler-Einstein metric implies that X is K semi-stable. I'm not going to define this, but this in turn implies that this canonical extension is minus Kx semi-stable. So what is the relation between this Kähler-Einstein metric and this extension? Well, let me rather tell you about the implication K semi-stable implies Ex minus Kx semi-stable. This comes from an estimate on what is called the greatest lower Ricci bound. So this really has to do with some differential geometric arguments and estimates, from which you can estimate some slopes. Okay, let me also say that none of these arrows is an equality. So there are K semi-stable smooth Fanos which have no Kähler-Einstein metric, and there are manifolds, Fano manifolds, where the extension is minus Kx semi-stable, but where the variety is not K semi-stable. And before giving you an example of this for this last non-arrow, let me mention that if I allow singularities, so for X Q Fano, the existence of a singular Kähler-Einstein metric in the sense of Essidieu, Gedge, and Seriari mentioned by Henri yesterday implies that this extension is still minus Kx semi-stable, and that's a recent result of Druel, Guenancia, and Paul. Yeah, so also in the more general and also maybe more interesting singular Q-Fano case, having the singular Kähler-Einstein metric guarantees that this extension is semi-stable as a sheaf. Yeah. So the counterexample up here is provided by a very classical sort of variety, sort of classical algebraic geometry, namely you take the Grassmannian 2,5, so Grassmannian of planes in C5, you embed it into P9 via Plücker embedding, and then you take a general linear hyperplane section. And then this has semi-stable canonical extension, but as a variety is not K semi-stable. And in particular, it does not admit a Kähler-Einstein metric. Okay, so this is really a more general and, okay, I maybe have not enough time to do that, but also compared to K semi-stability, very easily checkable condition. Yeah, so to check that this canonical extension is semi-stable as a sheaf, if you have, for example, this hyperplane section of this Grassmannian, you just use standard exact sequences and some vanishing results on Grassmannians or something, and then you're done. You can prove that. Okay, so now that I have this inequality, yeah, the proposition says that if Ex is minus Kx semi-stable, then the Miao-Kayao inequality holds. I'm interested in the boundary case, yeah, and that's the following theorem due to myself, Quebecus, and Peternel in this new preprint. So if I'm on a terminal Q-Fano, and again, you can replace terminal by KLT, such that this canonical extension is minus Kx semi-stable, if equality holds in the Miao-Kayao, then my space can be uniformized by Pn in the sense that X is of the form Pn modulo a finite group, where G, this finite group, acts on Pn freely outside, in this case, a codimension 3 subset. Yeah, because the terminal singularities are in codimension 3. The action is free in codimension 2. Okay, and yeah.
This in particular implies that you have this flatness conclusion, right? That the nomotisms of E has a flat metric or something.
That's true. We will see. That's how we prove this. Yeah.
Good.
So let me comment. I mean, we've been doing, I mean, it's really, I mean, I think this is really embarrassing in a sense for us. We've been doing this, this uniformization, or we've been proving or investigating these uniformization questions for a long time. And the first thing we did was for abelian varieties. Yeah, you remember Henri's talk, where in each of the 3 cases, so signs for the Kähler-Einstein metric, I mean, positive, 0, negative, there was some uniformization result after having some inequality. So we first did it for abelian varieties. Then we did it for the case of varieties of general type, where it's much more complicated because you cannot just look at semi-stable sheaves, you have to look at semi-stable Higgs sheaves. So you have to use Higgs bundles with non-trivial Higgs field. So that's technically much more complicated. And we always thought, or at least me, I always thought that if you want to characterize something with Pn, you have 2 difficulties. At first, this extremely complicated business regarding K semi-stability. And then I was expecting some characterization of Pn in terms of rational curves to come up. In the end, we use the following, in some sense, easiest and earliest characterization of projective space. So let's see. Yeah, this is the theorem of Kobayashi-Ochi, which so we use the corollary, but I put up the result here from which it follows. So this says, this is a statement about manifolds or or complex spaces. So if you have, say, a manifold with an ample line bundle, such that the top intersection number of this line bundle, so C1 to the F to the N is 1, and it has more than N independent sections, then M is biholomorphic to complex projective space, and this bundle is O of 1. No? Okay, and from this, so how do you prove this? You really just look at the map induced by the sections, and then you use this condition 1 to see that it has to be base point free and injective, and then you write down. I mean, you see that the H naught is not just bigger than or equal to n+1, but exactly n+1, and then this this map will give you an isomorphism to Pn. Yeah, and this has the following corollary, that if you have an n-dimensional compact complex manifold, it has to be Fano, because you assume that C1 of M is bigger than or equal to n+1 C1 of F, where F is an ample bundle. Yeah, so C1 of M, which is C1 of minus Km, is ample. Then M is actually biholomorphic to complex projective space. Yeah, so this means that if the anti-canonical is divisible by n+1 in the Picard group, then you're already projective space. Okay, we're going to use this very classical result. So in the proof, this means we're using this corollary. We have to arrange for 2 things. We have to manage to see that some finite quasi-étale cover of X is smooth, because in the end, my X should be Pn mod G. Yeah, so this means I have to find this quasi-étale cover, and then on this quasi-étale cover, I want to prove that that is Pn. And I have to find this ample bundle on X, or rather on the on this quasi-étale cover, satisfying this divisibility. Yeah, so that C1 of minus Kx hat, say, is equal to n+1 C1 of F. Okay, and I have to somehow derive these 2 points corresponding to the conditions in the corollary from my conditions, which is equality in Miyaoka-Yau after semi-stability. So this is done as follows. So you see it coming. I take this quasi-étale cover, which is maximally quasi-étale. This is this X hat. Yeah, so this has this the defining property, which does not define it uniquely, but that's all we need, is that every flat vector bundle on the regular locus of X hat extends to X hat. And this has some Galois group, which I call G. Yeah, so the thing to show now is that X hat is Pn, and then X would be Pn mod G. Yeah? Okay. So yeah, the goal, X hat is smooth. That's the first goal, X hat is smooth. So now these two lines tell you that the assumptions I made on the semi-stability of Ex and the equality in the Miyao-Kayao and the Fano condition, these are reproduced on X hat. Yeah, so say first, let me see, I said this. Yeah, so first, because my gamma is unbranched over the smooth locus, it's easy to see that the canonical extension on X hat is essentially the pullback of the canonical extension on X. The anti-canonical on K on X hat is the pullback of the anti-canonical on X. This in particular implies that the anti-canonical of X hat is ample and that the singularities are of the same quality as the ones on X, which is terminal. So, and then also the equality in the Miyao-Kayao is reproduced because essentially this the relevant quantity, the delta, is just multiplied by I think it's the order of G or the order of G to the n minus 2 or something. But if it was 0 downstairs, it's 0 upstairs. So all the assumptions are reproduced after this cover on X hat. Okay. So now, as X hat is maximally quasi-étal, the main flatness theorem, which I put down at the beginning of this lecture again, says that this endomorphism is sheaf is locally free and flat. Yeah, so this is exactly the condition. Yeah, so I'm on X hat, I'm on a terminal projective variety. I have this sheaf E X hat. It's still semi-stable because it's a pullback of this semi-stable sheaf, and I use the polarization which I obtain as a pullback, and it has a vanishing discriminant. Yeah, so and let me just put this up again. Yeah, so the conditions of this main flatness criterion are fulfilled. X is equal to X hat by construction. I have this F, which is my extension, which is pushed forward from the smooth locus, from a vector bundle on the smooth locus. It's semi-stable, and by construction or assumption, my delta is 0. Yeah, so what I wrote down here on my slides are exactly the conditions for the main flatness theorem. And so I apply it, which tells me that the endomorphism sheaf is locally free and flat. Okay, so what does this imply? So we call what this extension is. It's an extension of Tx hat by Ox hat. It's locally splittable. Hence, and that's now comes the point where we need that again. Locally, this extension splits. So locally, Tx hat is a direct summand of Ex hat. So locally, Ex hat is just Tx hat plus O. Yeah, and then if I then take the endomorphism of that sheaf, it's a tensor product of the dual with itself, I see that the tangent is a direct summand of Ex hat locally on this U where everything splits. Yeah. So Tx hat restricted to U is a direct summand of end. But then it's a direct summand of a locally free sheaf, so this means it's locally free. Okay, so what does this mean? It means that X hat is a terminal projective variety, so a projective variety with terminal, hence KLT singularities, where the tangent sheaf is locally free. Okay, and then this result of Druel, which I proved even, shows that X hat is smooth, and okay, by construction, X is X hat mod G. Yeah, so X hat I proved using this flatness and locally freeness of the endomorphism, which followed directly from the flatness criterion, and this observation of Druel that X hat is smooth. Okay, that's my first step. And so in the second step, I want to prove that x hat is actually Pn. And that's much easier than you think it would be due to the theorem of Kobayashi-Ochi. Yeah, so let's do it. So at this point, I only use that the endomorphism, up to this point, I only use that this endomorphism of Ex hat is locally free. Now I'm using flatness. So I know that this is isomorphic to this to a sheaf of the form G rho for some representation rho. Yeah. So again, since I have the time, let me recall what this G, how you get this G rho. Yeah. So if I have a representation rho from pi 1 of x hat to some GLR of C, then what do? I take the universal cover of x hat, I cross it with C to the R, and then I divide by pi 1 of x hat, where the action on a point on this tuple is just here. It's the deck transformation group, the deck transformation action on the universal cover, and here I take rho of gamma, which is an endomorphism of C to the R, and I apply it to V. Yeah? Okay, and this is the action, and then you see by some small invariant theory discussion that this here has a natural projection to x hat tilde mod pi 1 of x hat tilde, which is x, and this is a vector bundle. Yeah. Okay, so this is then the total space of G rho. Okay, that's how it works. So we have this sheaf, and then we know that the endomorphism is of this form. But now I was extremely happy when I saw that Henri had actually proved this. He proved that if I have a smooth Fano, so I am on a smooth Fano, x hat, that the fundamental group is trivial. Yeah, so I'm simply connected. So there is only the trivial representation of rho, and this means the endomorphism is not just flat, end of E x hat is trivial. And that's very, very good. And so let's think about what this means. So I have this E of x hat, and the endomorphism is the trivial bundle. So write out this trivializing isomorphism, say, over a trivializing cover for this E of x hat. Yeah, so this E of x hat comes with some transition functions, G alpha beta. Yeah, it's a vector bundle E of x hat, so it has these transition functions. And so if I write out this isomorphism phi, I'm writing an isomorphism from end of Ex, which has transition functions. So they're given by conjugation with G alpha beta. Yeah, so you see an end of Ex, these are endomorphisms of the fibers of Ex, and they transform by conjugation on the trivializing cover by conjugation with the transition functions that you have for E of X. Yeah, and so if you write this out, you essentially need as a condition, so phi, the existence of phi forces essentially, yeah, it's not true on the nose, that G alpha beta of X times A times G alpha beta inverse of X is A for all A, which are the endomorphism, linear endomorphisms, and for all X in the intersection of U alpha and U beta. Yeah? But this means that your transition functions, if you evaluate them pointwise, they're in the center of end, which means that they are diagonal. Yeah, so this means that G alpha beta maps from U alpha beta to C star times the identity. Okay, after changing coordinates, yeah, this is what I suppress. What does this mean? This means that E of x hat is not just a vector bundle, it's a direct sum of line bundles. Yeah. And the transition functions for the line bundle are these G alpha beta, which now take values in C star. Yeah? So this means that Ex hat is a direct sum of rank n plus 1 of a line bundle, which I can compute from this G alpha beta. Okay, so that's where my line bundle appears. And now I check that the line bundle L plays the role of F in the theorem of Kobayashi-Ochiai. So as E of x hat is an extension, I recall again, of Tx by Ox, if I take the determinant, yeah, then on the one hand, where is it, my extension? It's here on the left. Yeah, if I take the determinant of this exact sequence, I see that the determinant of Ex hat is the determinant of Tx hat. I mean, that was one of the properties I already used in the formulas, but let me point it out again. So O of minus Kx hat is the determinant, but then I also know that E of x hat is this direct sum of L, so the determinant is also L to the n plus first tensor power. So what does this mean? This means that L minus Kx hat is a multiple of L, which means that L has to be ample because minus Kx hat is ample. And on the other hand, this is exactly the relation you need for the theorem of Kobayashi-Ochiai, that C1 of x, which is C1 of x hat, it should say, is equal to C1 of minus Kx hat, is n plus 1 times C1 of L. Yeah, and so I can apply the theorem of Kobayashi-Ochiai to get that x hat is Pn, and as I explained, this finishes the proof because then x is a quotient of x hat by g, and this action of g has this property that it's free outside of a codimension free subset by construction of this maximally quasi-étale cover. Okay, so I think this is everything I want to say. Maybe I can answer some questions on this if there are any. So the message here is that in a combination of sheaf theoretic methods that you extend from the smooth and locally free case to the slightly singular reflexive and terminal or KLT situation, together with a topological result on the local fundamental group of KLT or terminal singularities, you are able to prove these uniformization results under a condition which does not involve the Kähler-Einstein condition. And I want to point out that even in the smooth case, I mean, you could have done this proof, which I just explained, a long time ago, and maybe it was known, but I'm not aware of any place where it's written. This gives the new point of view on the Miyaoka-Yau that semi-stability of this extension is really the thing you need for the Miyaoka-Yau inequality to hold, and also to get this uniformization result or the characterization of Pn. And as I pointed out on this slide here on the right, the condition of Ex being K minus Kx semi-stable is somehow much more elementary, a much more elementary question than the existence question for Kähler-Einstein metrics or K semi-stability, as one could explain in certain examples, which you can also find in our paper, where, for example, we check that the following result. Let me maybe write this on the paper. Yeah, so we check in the paper, and this is not so hard, if X is a smooth Fano threefold with pk number 1, then Ex is always minus Kx semi-stable. Yeah. So this doesn't necessarily lead to a new result regarding the inequality and the characterization of Pn, because these uniformization or inequality results were known by just looking at the classification of these things, but it gives a new sort of conceptual maybe approach to this. And also, I want to point out that the last time I checked, which is not so long ago, but this field is fast moving, it was not known whether all these Fanos are actually K-semi-stable. Okay, let me stop here and thank you a lot for the opportunity to give these 3 talks and for your attention, continuing attention in your case through these 3 talks. So thanks.
Thank you.
Thank you.
Any other questions? Questions?
Yeah, this implication that K semi-stability implies that Ex is minus K semi-stable.
Yes.
It's like a pure algebraic statement. Is there algebraic proof of it?
I am not aware, and I asked Henri and also other people. I mean, other people much more involved in this case semi-stability business. They are not aware of a algebraic geometric proof. It's a general. It's a very, yeah. I think that's one of the difficulties in this case semi-stability business, that every now and then you switch to the analytic side and use the existence or almost existence of a Kähler-Weinstein metric to prove some implication between 2 purely algebraic geometric statements.
Okay. But say, what about positive characteristic? Did people look at it in that situation?
So I don't know. I mean, so very recently, and I'm really not an expert on this,
right.
I think Ahmadinejad and some other people, they found a method of checking K semi-stability by looking at certain, I mean, admissible flags coming from, I think, minus Kx and multiples of that. And then you have to check some condition on this flag, which looks more, I mean, so this is of a different flavor than this degeneration. I mean, the actual definition of K semi-stability requires you to check C star degenerations of your X. But then, I mean, I think the main progress that has been made that makes all of these subsequent stuff possible. Oh, let me see. I mean, probably it's Odaka. I mean, there is this equivalent formulation of, you see, some of these zoo of conditions. I mean, there's K semi-stability uniform versions. There is, and there are polar stability statements and so on. And there is a reformulation of some of them in terms of divisorial stability, which then is some statement which works more on the single Fano and some blow-ups and so on, and not on the degeneration. I mean, of course, in the background there are some degenerations, but you can reformulate and prove that you just check this, I mean, you check this divisorial stability on the original Fano with respect to some devices, or all devices. And then the question is, which devices are most likely or would carry instability, and then you only have to check those. And I think that's the stuff that people are currently investigating, but I'm really not the person to give the definite answer.
Right. Probably nobody yet can do it anyway. I mean, it's very much in progress. Yeah. Okay, thank you.
Sure, you're welcome.
Other questions? Okay, if not, let's thank Daniel again for the series of talks.
Thanks a lot.